Hi, this is Module 5 of Two-Dimensional Dynamics. Today's learning outcomes are to describe the kinematic relationship of acceleration in a tangential and normal coordinate system. Last time we did position and velocity. And then we're going to use those kinematic relationships to solve a particle kinematics problem in tangential and normal coordinates. So, going back to last class, we have this particle going along a curvilinear path. Its velocity is going to be s dot for its magnitude, the change in arc length with respect to time, and the direction is always going to be tangential to the path, e sub tangential. And so the acceleration is going to then be a derivative of the velocity. Both s dot and e tangential, the direction will change as we go along the path, so I've got to use the product rule. So I've got s double dot times e tangential plus s dot times the derivative of e tangential, or s double dot e tangential plus s dot, and I'm going to break, similar to what I did before, I'm going to break this derivative of e tangential with respect to time into two parts, a motion part, d theta dt, and a geometrical part, d theta t, or d of the e in the tangential direction, d theta. And so here, if I look at my particle at point P here, this is my x and my y coordinates. I have a tangential direction and I have a radial direction, or a normal direction, that I'll draw that's directed radially inward for the curved path that it's on. And so this is an overlay of those two coordinate systems. And so what I want to do now is I want to write E tangential in terms of I and j, and E normal in terms of I and j. And so I'd like you to do that, fill in the blanks here, and then come on back. So what you should have found is, okay, for E tangential, we're going to go out cosine theta, a distance cosine theta in the I direction, and a distance sine theta in the j direction. And for E normal, here's E normal, I'm going to go minus sine theta in the I direction, and plus cosine theta in the j direction. So what I can see from this relationship is real important. If I take the derivative of E tangential with respect to theta, I get derivative of cosine theta with respect to theta is minus sine theta. The derivative of sine theta with respect to theta is cosine theta. So I know that E normal then is equal to the derivative of E tangential with respect to theta. And so that's important because that's the result I need up here. So let's continue on. There's my velocity. I have now found that d theta dt, d theta of E tangential with respect to theta is E normal. So I know what this is. I still need to find d theta dt. And so for any infinitesimal segment of the curve along the arc length here, as this goes along a small portion of the curve, let's say that the radius of curves here, rho, is constant. So s, you should remember back from your math days, your basic math days, that this distance s that you go is equal to rho times theta. Okay? And so if I take the derivative with respect to time for an infinitesimal segment, rho doesn't change, so I get d theta dt equals 1 over rho ds dt. And so again, I can use that to put in here. And so I get a sub p is equal to s double dot in the E tangential direction, plus I've got s dot here. Here I've got d theta dt, which is s dot and 1 over rho. So I've got s dot here, s dot there, so that's s dot squared over rho. And we know that d theta, d of E tangential d theta is equal to E normal. And so that's an expression for the acceleration in the tangential and normal coordinate system. Another way to express it would be a sub p is equal to s double dot E tangential plus S dot, remember, that's the speed, or it's the magnitude of the velocity. So I can write this as the magnitude of the velocity of p squared over rho in the normal direction. And so this term is the rate of change of the magnitude of acceleration. Rate of change of the magnitude of the velocity, excuse me. So this is the rate of change of magnitude of velocity. And we call that the tangential acceleration because it's in the tangential direction. So this is the tangential acceleration. And this is the rate of change of the direction of the velocity. So this is rate of change of direction of velocity. And we call that the radial or normal acceleration. So this is the normal or radial acceleration. So in normal and tangential coordinates, we have two components: a rate of change of the magnitude of the velocity, not vection, but this should be velocity, and a rate of change of the direction. And so let's look at a small demo here. Here's a, let's say that this is a particle here, this ball, and it's moving along a curved path. And so as it moves along a curved path, if I speed it up, there can be a change in the magnitude of the velocity in the tangential acceleration, and the direction is constantly changing, and it's changing radially inward. So that's the normal or radial acceleration that's inward. And so you see both components of the acceleration of the particle. All right, let's go ahead and use that, that theory for the kinematic relationships in normal and tangential components or coordinates to go ahead and solve a problem. So here's the problem. We have a racing car, and you saw some racing car clips in my intro video, which I'm showing again here. And we're going to treat this racing car as a particle, and it's going to start from rest. It's going to go through a distance of 1 mile for 30 seconds and go into a curve with a radius of curvature of 0.2 miles. And I want to find the normal and tangential acceleration just before point A and just after point A. So let's start just before point A. And let's look at the normal acceleration first. We know that the expression for the normal acceleration is the magnitude of the velocity squared over rho. My question to you is, what's the radius of curvature just before point A if this car is moving along a straight line? And the answer should be it's infinity. And so no matter what the velocity is as we go along that segment, the radius of curvature is infinity, so the normal acceleration is equal to 0. Now let's go ahead and do the tangential acceleration. And so for the tangential acceleration, we're given that the tangential acceleration is constant. And so it's going to be given, I'll give it the symbol C1. Since I want to find that, and I know some information about the distance and the time, let's go ahead and integrate that and use this information that I'm given to go back and find what the tangential acceleration is. So let's start with taking that tangential acceleration, which is unknown, and integrating it to find the expression for velocity. So we know that velocity is the integral of acceleration tangential, which is the integral of c1 dt, or c1 times time plus some constant of integration c2. How do I find that constant of integration c2? And the answer should be use the IC. And so I'll apply the initial condition, and I get the velocity at 0. It starts at rest, so that's going to be 0 is equal to c1 times 0 plus c2, or c2 equals 0. And so now we have an expression for velocity. I want you to do the same thing for displacement, to find the expression for displacement. And here's what you should have come up with. The displacement, which I'll call S, is the integral of velocity, so it's going to be C1, a constant. The integral of t is t squared over 2, plus some new constant of integration, C3. I can use the initial condition for S, which is the starting point. We'll use that as our datum. So S of 0 is 0, or C1 times 0 squared over 2 is plus C3 equals 0. And so that means that C3 is equal to 0. And so now I have an expression for the displacement. I also know some more information. The position or the displacement at 30 seconds is 1 mile. So let's use that. So I have S of 30 equals 1 mile equals now C1 times 30 squared over 2. And that's going to now allow us to solve for C1, which is our tangential acceleration, which is what we need for the solution of part A. And so I get C1 equals 2.22 times 10 to the minus 3 miles per second squared, or I can express that as a vector now. A tangential, which is C1, is equal to 2.22 times 10 to the minus 3 miles per second squared, and it's going to be, the direction is going to be to the right. Okay, my question to you now is, looking at part B, what is the tangential acceleration going to be right after it passes point A? So if the acceleration tangential is 2.22 times 10 to the minus 3 miles per second squared just before point A, it's not going to instantaneously change. So it's going to continue to be that same value tangent to the path as we go into this turn. So the last thing we have to find is the normal acceleration. We know that the magnitude of the normal acceleration is the magnitude of the velocity squared at that point over rho. And we have an equation for the velocity. We found that the velocity was equal to A tangential times time. We know at this point we'll have gone through 30 seconds of time, so we have V equals 2.22 times 10 to the minus 3 times 30 seconds, which is going to end up being 6.67 times 10 to the minus 2 miles per second. And for my US students, that converts into 240 miles per hour. And I'll let my students outside of the United States convert that to kilograms or kilometers per hour. Okay, so now we have the magnitude of the velocity. So we have A normal is equal to 6.67 times 10 to the minus 2 over the radius of curvature squared over the radius of curvature. And the radius of curvature of this curve is 0.2 miles. And so this gives us 2.22 times 10 to the minus 2 miles per second squared. And so we have then the normal acceleration as a vector is 2.22 times 10 to the minus 2 miles per second squared, and the direction is going to be radially inward. And so that completes the problem. And so I have a practice problem for you to do on your own. It's another race car problem, and I'll let you work through this worksheet, and I have the solution in the module handouts, and we'll see you next time.